let me say a couple of words about the homework.
Exactly.
Don't forget Monday's the learning day. Sometime over the weekend, I will record lecture, post on Wednesday. If you need help, to be posted, for Monday's class. If you need help, on Monday, I'm working at home doing working on other stuff, but just get a hold of me somehow. However you get a hold of me, email or whatever, and I can even get on Zoom or whatever. So here's the next homework. It's not too long of an assignment, I don't think. The R module F, so we're going to talk about free modules, but this is kind of a simplistic way that I can define them. I say that a module is free of rank N if F is isomorphic to a direct sum of a bunch of copies of R. So this is what I'm going to call free. And rank N means N copies. But in general, free module can be quite big. And this includes the zero module too. Suppose that M is an R module generated by M elements. So you've got just some R modules generated by M elements, X1 up to Xm. Show that if F is a free module with rank F equal to N greater than or equal to M. And since I did say N, you can assume it's finite, but this even works if this is an infinite rank module. Show that there's a submodule K and F such that F mod K is isomorphic to N. This is absolutely astounding, right? Because if I give you any, one of the things this theorem tells you is if I give you any module that's generated by N elements, right, then it's the homomorphic image of a free module generated by N elements, right? So that is, I can find a submodule of a free module of N elements such that that quotient is exactly equal to the module I started with. So in a certain sense, this is why free modules are going to turn out to be quite important, is any module can be realized as a quotient of a free module where the number of generators here coincides with this, or it's greater. Number two, we say that the R module P is projective, and again, we're going to get into this a little bit more fancier. If there's a free R module F and another R module K, such that P sum K is isomorphic to F. So what it means to be a projective module is its sum into a free module. Now, I know that there's probably some people say, okay, what's the point of this? Because, well, this one should be pretty easy. Show that any free module is projective, given my definition, should be easy. Explain why the module K in the definition up here is also projective. This time there is a reason they're worth 3 points. Show that Q is not a projective Z module. And number D, give an example of D is actually kind of important. Give an example of a projective R module that is not free. Now, when you give me such an example, you're going to need to give me two things. You're going to have to give me the ring R, because there are some rings, for example, fields, over which every projective module is free, and there are others as well. So you're going to have to specify the ring. But there's actually a pretty small example of this. Number 3 is a problem that I warned you was coming. This is part of the 5 lemma. Consider the following diagram of R module homomorphism with exact rows. The following 2 statements are true. G2 and G4 are onto, and G5 is 1 to 1. Then the middle guy is 1 to 1. So this generalizes that short 5 that we had. If G2 and G4 are 1 to 1 and G1 is onto, then the middle is 1 to 1. Pick either one and prove it, right? Right. Do them both for fun. Turn one of them in. That's what I'm going to do. Any questions? All right. Okay. All right. Any questions from last time? Okay. You thought we had fun last time. You didn't see nothing yet. So last time we did we did the short 5 lemma, which I hope everybody can kind of piece together. This one is,
The Sudoku.
right. Yeah, definitely. I'm actually, can you guys see this board here? I think I might just draw it up here to kind of keep it permanently. Too bad for the folks out there and, no, maybe I can use it. So 0, 0. I need a giant stamp or something with this on it. I guess it probably is better for me to put this on this board so that, watch the recording later. Here I'm going to suppress actually drawing the functions here. So let's suppose I'm going to tell this 1246. Suppose we had the following diagram. And I should say commutative diagram. And I want it right. Got it. Our homomorphisms. And I'm going to throw this in so make it easier here. With exact columns. So the columns are exact. Number A. If the column, well, okay, in the bottom 2 rows, okay, top. If bottom 2 rows are exact, so is top. And B, if top 2 rows are exact, so is bottom. Actually, maybe. Oh, I'm not remembering this up here. So this is, as you might guess, well, I don't know if you guess this or not, it's called the 3x3 lemma. So it kind of looks like the Hollywood squares. And this actually is quite important in some aspects of homological algebra. So is that columns? Okay, so I think that nobody should be denied a good diagram chase, including me. And so I'm going to prove one of these, and I'm going to leave the other as an exercise. But I'm going to show my truly lazy results by saying it's going to be your exercise, because I don't want to be reading crap you have to write like this. Okay, Sophia, Pick one. Can we prove A? Prove B. They're very similar. In fact,
A.
okay, so let's prove A. I'll put this in quotes because I might, just kind of thinking through the diagram checks a little bit. Okay. I always forget which one is hard. So what we have here is we have the bottom two rows are exact. We need the top to be exact. So for this one, exact, exact, and we'll show this one here. And then the columns are all exact, right? And the diagram is commutative. So that means if I start here, it doesn't matter how I go to here along the arrows I've written, I'll get the same answer, right? That's the commutative diagram. Okay. What do I have to show that the top row is exact? Well, essentially 4 things, I think. I need to show, so I will write this down here, F, G. I need to show 1. Kernel of F is 0. That is, I need to show that's 1, 1. Number 2, image of G is A3. I need to show that this is on 2. I need to show kernel of F is contained in the image of G. And number 4, the image of G is contained in the kernel of F. So basically, the first thing is exactness at A1. The second thing is exactness at A3. And the last 2 combined is exactness in the middle at A2, right? Everybody with me on Saturday? Yes.
The kernel of F is in A1, but the image of G is in A3. Right?
Yeah, that's right.
So how would the kernel of F be in the contained?
Oh. Yeah, see, I've already got these up here. Yeah, it's seriously, again, with the beer and the aluminum can, image of F contained in the kernel of G, and kernel of G is contained in the image of F. There we go. Thank you. Right. Better. Okay, those last 2, of course, are exact as they too. And let's see here. Yeah, I think the first one's gonna be the easiest one, but okay, so let's start here. Let's prove this. Let X be in the kernel of F. So what does that mean? That means that X goes to 0 here. Agree? And X goes somewhere here. And B1, where does B1 have to go? It has to go to 0, that's right. Because following B1 like this is the same thing as going here, and I don't know much, but I know that 0 has to go. Do I agree with it? So, what does that mean? What do we know about this row? It's exact. So if B1 goes to 0, because middle row is exact, B1 must be equal to 0, because B1's in the kernel of this map. Do I agree with that? And this is 1 1, so B1 has to be 0, right? Therefore, X goes to 0 vertically. So B1 is 0. Well, what do you know about this? It's also 1-to-1 because the columns are exact, right? Uh, so that one we pounded out for you. Right. If I agree with that. Okay, let's do onto of this one. This one's going to be real painful. Everybody with me so far? Forward here. Now I want to show that G3, I'm sorry, the G is onto. Okay, two. Oh, this was going to be fun. Let I've got to find something that goes to it. Everybody agree with that? Non-offensive red. So I need to show this onto. Now, the good thing about this is there's kind of only one way to go, right? Of any significance. I don't know much, but A3 goes down here to B3. Now, of course, I can compose this again. Well, what's going to happen if I compose B3 again? I should get 0 because the columns are exact. So when I push it twice, I should get 0. So maybe that's useful later, but let me do something that's got a little bit more teeth to it. What do I know about this map right here? It has to be onto, right? Because the sequence is exact. So there's B2 that goes here. Right? I think I am going to get that B3 push on to 0. So let's push this on here. And the reason I think that is because I'm really jonesing to go back up here, right? But there's no reason to think that I can't, right? I mean, what do I know about this map? I know it's 1-to-1. That's kind of it. But what happens when I push this way? It goes to some C2, right? And where does C2 have to go? C2 must go to 0 because the diagram. So this B2 here, notice, by the way, my choice for B2 is probably not well defined because when I took that B3, I know I don't claim that this is a function. There's just something that goes to B3, right? But whatever that something is, I don't care what it is, goes to B3 and to 0 this way. So it has to go to a C2 that goes to 0, right? Looks like I'm running out of real estate fast, but there is one saving grace here. Anybody know what it is? What can you now say about the C2? C2 is in the kernel of this map, so it must be in the image of this one. So there must be some C1 that goes to C2. Look how far away I am, right? This is looking like it might be hopeless. Well, I still feel like I can keep going, right? Because this is onto, this columns are exact. So there's B1 here. Agreed? By a piece. All right. Well, there's no reason to suspect I can go back this way, so let's do this. This goes to everybody agree with that? I don't know much though. See, B one goes to B two prime, but I do know, where does B two prime go when I push it down here?
Oh, it has to go to C two,
It has to go to C two. Why?
commutative.
The commutativity of the diagram. B one goes this way to C two, so whatever this goes to, B two prime, it has to go to C two. Do I agree? Okay. Now what? Sometimes this comes up in diagram chasing quite a bit. That's, as you see, I've written a lot of details over there, so I'm gonna throw this one in. Let me call this map something just for utility's sake. Let's call this, alpha. Alpha B2 equals alpha B2 prime. Agree? That means that alpha of B2 minus B2 prime is equal to 0. And what's the utility of that? The kernel, and let me call this something. I'll call this beta. Exactness of the middle column. So there exists, let's say, A2, right, such that beta of A2 is B2 minus B2 prime. So there's an A2 here. It goes to B2 minus B2 prime. Am I okay with that? Okay, so how do we push forward here? I'm gonna call this gamma and delta right here, this map, this map. What happens when I do this? What happens when I take A2 and I go this way? That is, I go G and then delta. Isn't that the same thing as taking A2 and doing beta then gamma? Am I agree with that? Now let's see what happens. Beta takes this to right? Now what's gamma of B2? It's B3. Everybody agree with that? Can you tell me what gamma of beta 2 prime is? That is correct. It's 0, right? Because remember, B2 prime is in the image. So when I hit that again, I have to get zero, if I agree. B2 prime comes from B1, and when I do gamma to it, I have to go to zero. Great. So let's see what we have here. We have delta G A2 is B3. What do you know about, right. What do you know about, well, and let me do this way. And this is also, B3 is also delta of 8. Do I agree with that? B3 is also where A3 went. And what do you know about delta? Delta is 1 to 1. Now that's a chase that isn't fooling around. Notice that I pretty much visited everywhere except for maybe A1. Well, A1, right? So remember how easy 1 to 1 was? I just needed this box, right? To show this is onto, you dance all over Hell's Half Acre, right? Yes.
Would you just be able to explain why B2 prime, gamma B2 prime is 0?
Right, because remember what B2 prime is. It's B1 going here. Now, if I do B1 going here and then do again, because the image of this is the kernel of this, that means that B2 has to go to 0.
Okay.
It's the exactness of the middle. Everybody okay with that? So Sophia, you picked A, which was, we're trying to show the top is exact, give the bottom 2. Anybody want to venture a guess what to happen if she had picked B, right? So now the top 2 are exact, now the bottom row is exact. So you should probably work through this yourself with follow way. For us, 1 to 1 was easy, onto was a bit of a dance. If Sophie had picked a different one, 1 to 1 would have been the dance, and the onto would have been easy, right? They dual out that way, which is kind of cool. For the other ones, almost always with these kind of things, this one's fairly easy and this one sucks, but you know, we'll get through it.
Dr. Gordon?
Yes,
That middle line there, could you explain that, please?
right here.
Yeah, okay.
So, oh good, I've got everything here. Start with A2.
Yeah.
Do G and delta to it, and you get to B3,
Yes.
right? Because that's, and also, start with, A2 here, do beta, then, gamma.
Yeah.
Right, which
So
is,
you end up at B3 minus 0.
right. And. Right, so do you get it now or sir?
You get to B3, but then how do we?
Because that was the very first step. Right.
But
A3 went to B3 via gamma.
Right, but how do we know that A2 goes to A3?
We don't, not until the very end. Right? All I know is A2, do G, right, so
So our first step was set.
I'm not
A3.
claiming this is A3 at this point.
Right,
Right, this is just some, this could be something different than A3. But by the one to oneness delta,
okay.
it shows it has to be that. Right, yes.
So is the first function, like F is 1 to 1, and then G is onto it?
We know that now.
Okay, so it's always the like, for exact ones, it's like the first one is 1 to 1.
That's right,
Okay.
that's right. 1 to 1, onto, and then exact in the middle. All right, everybody okay with that? Okay. This works out very well for me. All right. Alright, so. Alright, let's see, we'll figure this. Okay, so let's do the easier one, because that'll require less me erasing. Let's do image that. So basically, all we have to do is show that if we compose stuff two in a row, we get zero, right? So start with A1. Let F jump it to A, actually. Color here. Let's start with F. A1 goes to A2, jumps to A3. Our burden of proof really is to show that A3 is C. Right? That's what we have to do, is to show that the image is contained in the kernel. That's all we got to show. Everybody okay with that? So let's see what happens here. This goes to B1. This goes to B2. Right? And if I compose this again, this goes to zero. Right? Because I know that that middle row is exact. Right? Now, here's what I know. I know that A2 right. I know that A2 goes to A3. Let's see. I'm not going to sing this.
Dr. Gordo,
Yes.
if you just send A3 to 0 via delta, and then delta is 1, isn't that it?
Well, right. Let me explain myself here. Actually, A2 does have to go to B2, because if I start with A1 here, go to A2, go down here, this has to end up at the same place this did, right? So A2 definitely goes to B2. Right? And B2 goes to 0. Well, by commutativity of the diagram, A2 goes to A3, which goes to 0. So in particular, delta of A3 is equal to 0, which implies A3 is 0. So image of F is contained in the kernel of G. Normally, that containment is usually not too bad. And it certainly wasn't too bad here. How about the other containment? Let's let X be in kernel. So, I want to chase a little bit. Okay. F, G, it's called beta, alpha, gamma, delta. Okay, so let X be in the kernel of G. That means you go to 0 here, period. Right? Now, of course, what I'm trying to do is I'm trying to get back here somehow. I've got to work my way back to A1 and find something that goes to X. And really, the only thing I can do at this point, I guess, is go down here to B2 and here. And I'm going to use the commutativity of the diagram to now observe that since this goes to 0, B2 goes to 0. So in other words, B2 is in the kernel of gamma. So that means there's something that goes here. Great. Well, I need to somehow get to this top row. So what I'm going to do is let me observe that B2 also goes to 0 this way. All right. Because of the exactness of this column. Start with X, B2 on 0. So that means that this must fold over to 0 this way. Right. Now, what do I know? I know that this map here is 1 to 1. So I can record that C1 equals 0. Because C1 goes to 0, but the map is 1 to 1, so I'm going to call you 0 because that's what you are. All right. So that means B1 goes to 0. So by the exactness of this column, there exists an A1 that goes to B1. Okie dokie. Now to finish this off, let's follow A1. Now, unfortunately, I don't know that A1 goes to X. All I know is it goes to A2. Right? By the commutativity of the diagram, A2 goes to B2. Right? Yes.
How do we know that C1 is 0?
Because it goes to 0 here, and this is 1 to 1.
Oh, okay.
So what do I have here? I have beta of A2 is equal to B2, and that's also beta of X. Because X goes to B2 and A2 goes to B2, right? I agree. And so what can we conclude? What do we know about beta? Since beta is 1 to 1, A2 is equal to X, but A2 by definition is F of A1. So the kernel of G is contained in the image. Any questions on this? This is called, and I think with all my colored marker stuff up there, it's probably pretty obvious. It's called diagram chase. Try to do the dual one, right? Where you know the top two are exact. See if you can prove the bottom's exact. You will get a very similar proof, except for the hardness roles of 1 to 1 and onto will probably be reversed. Okay, any questions on that? Okay, so here's another one that it's important to kind of expose you to this. Consider the following diagram with exact rows. This is actually a fundamental, this is called Snake Lemma. How many of you have ever heard of the Snake Lemma? I've heard it passing. If you're lucky or unlucky, depends on the perspective, you might hear about it coming up in analysis class, in the methodology class. Because actually this is an important tool in homological algebra which, in algebraic topology, this is a big tool for, figuring out invariance of spaces, right? Using these algebraic homological tools in algebra, it's easy to use these algebraic gadgets to do things like show that a sphere and a torus aren't homeomorphic, right? Do you all know all those words I used? Homeomorphic, okay. I challenge you to do that from first principles, right? Just to take a sphere, take a torus, and show that there is no one-to-one and onto continuous function with a continuous inverse from the sphere to the torus. I challenge you to do that. It's not so easy. However, applying some of the tools from algebra, you can attach algebraic objects to these topological spaces. And if they're homomorphic, the algebraic objects have to be isomorphic. And in this classical case that I spoke of with a sphere and a torus, well, one of the algebraic objects that you can attach to the torus is the first homology group, which is a direct sum of two copies of Z, right? And for the sphere, it's trivial. So those two groups are isomorphic, so the spaces can't be homeomorphic. Yes.
I don't know all of those words that you're using. So just a question about like stuff like for the exam, are we expected to know like topology and real analysis terms as well, or?
No.
Okay, great.
I mean, I'm not gonna, right. Yeah, surprise. What's a clopen set? No,
Oh, no.
So there. So. Call. Sometimes it's certain. Consider the following commutative diagram with exact rows.
Dr. Oshel,
Uh-huh.
is this category theory?
Well, not really. But, I mean, category theory is much more general. This is really, I'm couching this in terms of R modules and R module homomorphisms. A1, what's something A1, A2, A3, 0, 1, 2, 3. F's. I'm not going to go through it from proof of this, but I'll hopefully give you an idea of how this works. Then there exists an exact sequence. Kernel G1, personal G2, kernel G3. There's a snake, co-kernel, co-kernel G2, co-kernel G3. And I want to call these something alphas. And yeah, I didn't tell you how the alphas are defined, but I'll show you. Additionally, if F1 is 1 to 1. F1 is 1 to 1, so is alpha 1. And if H2 is on 2, so is beta 2. So let me remind you here, in case it's not just rolling off your tongue. Call if F made to B is an Armand homomorphism. Actually, it doesn't have to be an Armand homomorphism. You might have seen it somewhere. How many of you have seen the co-kernel defined somewhere? Maybe none? Okay, well, we'll fix that. The kernel of that, I think you're familiar with that. This is the set of graph and A such that F of A 0. I should think goes to N. And the co-kernel of F is B mod image of F. So the co-kernel is just whatever the target is, B modulo whatever A covers, right? That's what the co-kernel is. So in other words, you can write this as, for example, the co-kernel G1 is B1 mod image G1. And this is B2 mod image G2, and this is B3 mod image G3. That's another way of thinking about it, right? I used to assign this occasionally. Occasionally it depends. I will assign this to an Algebra 2 graduate. I hate to grade it, so I don't always assign it. I used to tell my graduate students, how many of you are movie buffs? So you might do this. You can actually probably look this up on YouTube, even if you're not. There's this movie from like probably the late 70s, maybe 1980, called It's My Turn. Ever heard of it? Yeah, it's got Jill Clayburgh and Michael Douglas. It's this awful movie about Michael Douglas is like this irresponsible baseball player, you know, like a man-child midlife crisis thing. Jill Clayburgh plays this college professor. And in the opening scene of the movie, she's a math professor. She's teaching a graduate class and she's proving the Snake Lemma. They actually did this in a movie, so she's up there proving the Snake. And of course, there's some snotty graduate students saying, "Oh no, it's not well defined." You know, just keeps picking on her, and of course, he's always just, you know, he's always wrong, and she has to correct him. And she goes through as much as she could do in a movie, a pretty complete for a movie explanation of Snake Lemma. And I used to tell my graduate students, "Don't come to my office and ask me about this. You can look this part of the movie up." But if you do this and look up the proof of the Snake Lemma on YouTube or whatever, your punishment is you have to watch the whole movie. And believe me, you do not want to do that. It's pretty awful. And that's kind of for me. So the Snake Lemma, basically the way this works is you've got this. What does this mean really? This means this is a short exact sequence with the defect is this one might not be 1 to 1. And this is a short exact sequence, and the defect might be that this is not onto it, right? What are you doing here? How does this work? Notice kernel of G1 is contained in A1, and the kernel of G2 is, so really what this alpha 1 is it's just F1 restricted, right? That's all it is, right? The kernel of G1 is just a submodule of A1. This is a submodule of A2, this is a submodule of A3. What you're doing is you're doing the map induced by this, right? So you take an element of the kernel and you apply F1 to it. The reason you end up in a kernel depends on exactness, right? Because it's not clear that if you take something in the kernel here, it ends up in the kernel here, but the sequence is exact. And so you have to check that detail. And these are all cool. The co-kernel is similar, right? You just move, you use this map, for example, take an element B1 mod the image of G1 into B2 mod the image of G2 by using the H that takes the coset representative here to here. Now, of course, you have to check that this is well defined, which is a pain in the butt, but it's not too bad. The exactness sets you up for it. The real interesting part, and this is the snake part, is how is it that you can get from the kernel of G3, so that's something that goes to 0 here, and get it to barf out an element of the co-kernel of G1. So something in B mod the image of G1. Here's what you do. It's in the kernel here, right? So it goes to 0. This is onto, so there's a pullback, right? This is not, there's many things that go to it. When you go here, the diagram commutes, so it goes to 0, which means there's something back here that goes to it. So you take that coset representative. Now that is soup's flaky because this choice is not well defined. And how does this work? I'll explain that a little bit of that later, but it's truly a miracle that you can serpent yourself, you can snake yourself from something that goes to 0 here, back to this element here and call it a coset and make that a well-defined map. That is the bridge, that is the snake. Okay, you all have a great e-learning Monday, and stay safe. Any questions? We'll catch you next time.